This video, we want to discuss high-pass filters, which, as you know, are filters that pass voltages from input to output at high frequencies. And so we're going to start by looking at the series RC. Once again, we are still discussing passive filters, meaning you have only passive elements, R's, L's, and C's. And we're discussing first order filters, meaning your transfer function will have a single pole, and so that's known as first order behavior. The pole will actually, once again, be equal to negative the cutoff frequency. So we'll go through the RC in more detail than the RL, but the RL is completely analogous and is analyzed in the same way, and we will show it at the end of the lecture. So here's the series RC circuit. In the case of the high-pass filter, we're taking the voltage output across the resistor. So thinking about that qualitatively, at DC, the capacitor is an open circuit, and so all of the voltage drops across the capacitor. There is no output voltage at DC. At very low frequencies, obviously, it begins to get a little bit of a voltage drop across R, but C is still looking like an open circuit. As frequencies get very high, the impedance of the capacitor, 1 over j omega c, as omega gets very large, so at very high frequency, recall the capacitor looks like a short, meaning all of the voltage will drop across the resistor. So the actual curve for the high-pass filter looks something like the one shown here in blue. It actually looks exactly like the one shown in blue, where the dashed line is, if you recall, our ideal filter, flat in the pass band, 0 in the stop band, and infinitely steep transition. Notice we don't have any of that here. We're 0 at DC, but then we immediately begin to have an output voltage. This point right here is the cutoff. Once again, it's defined at the half power point, which is when the magnitude of the transfer function is equal to 1 over the square root of 2. So that's just a qualitative look at what the magnitude curve of output over input as a function of omega will look like. Shown the phase here just for practical purposes for you to have seen it before. So let's look and see a little bit more of a quantitative analysis. So here we've transformed the circuit into the S domain. The capacitance has gone to 1 over SC. The R remains R. Input and output are functions of S. We find the transfer function, which we actually already did in lecture 1. We then do our step that we do when we're finding frequency dependence or frequency variation in the transfer function, is we now substitute j omega for S. So in this function, we've substituted j omega for S. We then find the magnitude of both numerator and denominator, which gives us the following magnitude function of j omega, and we find the phase. The phase of the numerator, because it's imaginary only, is 90 degrees. The phase of the denominator is the inverse tangent of real part over imaginary part, and so if we do some simplification like that, imaginary over real. So if we do some simplification on that, then we get the following for the phase. So basically, if you have complex number, and this is your phase, then this is your imaginary, and this is your real. And so if you take imaginary, which is j omega, and you divide by real, which is 1 over RC, and you take the inverse tangent, then you'll get this angle. So that's where this phase angle comes from. And the 90 degrees, the imaginary is J, the real is 0, so we can actually do that one by inspection if we want. So this is your magnitude of your transfer function. Remember that your cutoff occurs when this magnitude is equal to 1 over the square root of 2. So that would be here. That occurs when omega is equal to omega c. And if we solve for omega c there, we get 1 over RC. Note that that's the same cutoff frequency that we had for the low-pass filter. So we actually have our pole located in the same spot. The thing that's different in the transfer function is what the numerator looks like. So the cutoff frequency, the behavior in the time domain as far as analytical function is similar, but the numerator, the fact that you have an S term in the numerator of the transfer function, changes everything and takes what would have been a low-pass filter and changes it to a high-pass filter because of what's in the numerator. All right, here is the RL circuit. This is completely analogous to what we've done. I don't want to get too redundant in these videos, so I'm providing all the slides for you, and this is taken directly from chapter 14 of your textbook. It's actually a very good readable chapter, so I really highly recommend, especially on the section on RL and RC circuits, reading the chapter. Sometimes I think the textbooks present things in an odd way, and it might even make it more difficult to understand, but in this case, I think it's a very good chapter of Nielsen. So this is the example of the RL circuit. We have our input, we have our output. We take our output across the inductor. I'll just walk you through really quickly. You know, at high frequencies, or at low frequencies, inductors look like shorts. So at low frequencies, that output voltage is going to be 0. And then at high frequencies, if our input is high frequency input, inductors tend to look like opens. So all of the voltage will drop across the inductor. So qualitatively, it's easy to see how this is a high-pass filter. As far as deriving the algebraic expression, taking exactly the same approach that we took in the past, we've actually already done this. Use the voltage divider to find the transfer function. Then we substitute j omega for S because we're only interested in the frequency response. Here is what that S domain equivalent circuit looks like. We then take our function of j omega and we first find its magnitude, and then we set the magnitude equal to 1 over the square root of 2 in order to get the cutoff frequency, which once again is R over L, which is the same cutoff frequency as we had for the low-pass filter, only because we are taking the output voltage across the inductor and not the resistor, we're actually creating a high-pass filter. So these are actually not difficult forms to commit to memory. We can make a generalization that if we have a transfer function that looks like this, we basically have a circuit that is acting as a high-pass filter where omega c is the cutoff. So you actually, and this is an important point to make because we're going to do this as well when we talk about Bode plots, you can actually read the transfer function in the Laplace domain by inspection and note what kind of filter you have. If it's of the form S over S plus omega c, you already know that this will be the cutoff frequency and that this function will be acting as a high-pass filter. At this point, you don't even have to plug in your j omega in order to deduce that, because now you've seen it and you know the general form of the transfer function. So one comment is, when would you need to use the transfer function in this form for the magnitude? The only time that you really need to use this, once you're past the design phase. Let's say, for example, you want the exact value of the transfer function at a specific frequency. In that case, you just plug the frequency in, you know what R over L is, and you calculate that directly from the magnitude of the transfer function. And by the way, that is the case for any and all circuits and filters. If you want to know the behavior of the system at a particular frequency, then you find this magnitude of h of j omega, and you plug in the frequency, and that'll give you the response. In fact, you can even do it into the complex form, plug in your omega here, and then you can get both the magnitude and the phase, because sometimes phase is important. Okay, so that concludes our discussion of first order passive filters, both low pass and high pass. And at this point, you should be able to analyze and or design either an RL or an RC, either low pass or high pass, for a specified cutoff frequency. So we have not yet discussed using these in a circuits application, but basically that's your transfer function introduction and your introduction to first order passive filters.